Swayam Prabha. Digital India. Educated India.
Yeah, okay, there are all kinds of stuff out there. Hybrid of these methods, hybrid with even point-based. Yeah, but there are so many of them. I've decided not to talk about even any one of them, but these are basic ideas. Now, if you are going into that mode, you got to have a reason why you are going for hybrid. What is wrong with these methods that cannot be applied? And there could be reasons. So a good understanding individual methods like this will help you combine. Maybe you find PSO is good for certain problems, GA is not, but initially maybe GA is good, but then ending up with PSO may be good, so you can combine. So there should be a reason why you are using a combination. But I agree that there are a lot of stuff like that out there. Okay, but these basic things will help you read some of these papers, and then you try to appreciate or understand why they are doing that way. Any other question? All right, now we're going to switch gear to probably rest of the course we're going to concentrate on multi-objective, because I believe this is more general versions of optimization. A special case is single objective, but most books and papers are done the other way. They do single objective for most of the book chapters, and at the end they talk about multi-objective. Even I have done that, but that is because the tradition is like that, but I'm trying to change it by emphasizing more on multi-objective. You will see what I mean. So I've already introduced you this figure. If you have two conflicting goals, like here you have cost, which is going to give you one kind of solution, very simple, not much fancy. It comes at the expense of another objective, which could be safety, comfort. But if you want to do a good solution for comfort, it may look like this. A lot of extra things that are out there, that's going to make it costly. So that's the kind of trade-off. And in practice, we have full of these kinds of conflicting considerations. You cannot just design it for one, everything. Although I was giving a talk in a Navy shipbuilding, kind of ship manufacturing company. They wanted to know what is multi-objective. So there are a lot of gray hair people sitting in the front. And after my 40 minutes of talk, one of the gentlemen stood up and said, everything you said about multi-objective is not valid in our domain. I said, why? He said, we could put every objective a dollar value. So if you say cost is already some dollar value, comfort, can you put a dollar value? Maybe sometimes you can, but this will be a subjective thing, right? So if you can put an equivalent dollar value to, let's say 40% comfort means $1,000 or maybe $5,000. 50% maybe $6,000. So if you can put something like this, then you can simply add and say, I'm trying to minimize the sum of the two. Then everything is single objective. But if this comes to like life lost, like in a war scenario, or any of the other things like environmental effects, how can you put a number, dollar number to environmental, how it affects us? It's very difficult, right? So I believe they're saying it because they are not used to, and they've been doing this. But with the current kind of sentiments about various groups of society, keeping things separate, everything is important, you get more into these kind of multi-criteria scenario that you want to keep. So if I have two solutions, one has more lives lost, but cheaper. On the other hand, another one has less lives lost, but it's more expensive. You can now evaluate in terms of individual metrics, not kind of giving a combination of numbers. I think that's very fair way of doing it. So you are going to then going into more than one criteria, right? Okay, so I've got this book written in 2001 talking about some of this philosophy and the early literature on this. This is still good if you are interested in basics and foundations. All right, so All you have here in the NLP formulation is more than one objectives, as you see. Okay, constraints are still there, defining if you are feasible, variable bounds are still there. Okay. To this group, I think I can take this example. It's a small cantilever beam problem with a circular cross section at the end. Even if you don't know the context, is not a big issue, just take it like a numerical problem. We apply a load here and I'm trying to minimize the weight of this. So this is the weight I want to minimize. There are two variables, d, diameter and the length. Okay. And then the second objective is the deflection here. Because of this application of load, it's going to deflect. I want to minimize the deflection. And that brings in the Young's modulus and the load you are applying and so on and so forth. And then there will be stress that develops here and I want to restrict it so it doesn't break. And then I also want to restrict the deflection here with the delta max. So these are the two constraints. I took this very small example, the two variables, two objectives, so I can show you these plots. So what's happening here? This is the variable space called variable space, where I have d on this side and L on this side, two variables. I take lots of points here. For every point I have a d and L. I can compute the two, but before that I can see if it is feasible with respect to both of these. All these points here are feasible, these points are infeasible. That's why I didn't put the dot. Each of these points now I can compute f1, f2 and I put it on this space called objective space, right? And you can see that each of these points makes a kind of character to this region, okay? They are not all over the space, they are falling in some way. Now that's the entire search space here. I'm going to be searching here. This is the feasible, this is the boundary. There are two constraints, okay, boundary. And this is the objective space. Now looking at the objective space, can we say where is the Pareto optimal set? Because in these problems, Pareto set is the one, that red line that we are showing about, right? So I'm trying to minimize the weight, F1, I'm trying to minimize deflection. I want to go this way, I want to go this way. So where do you think is the minima, the Pareto optimal set? It cannot be here because this is bad for weight, bad for deflection. It has to be on this corner. So you remember what happened here? I told you that this will be my ideal scenario if I can get a point here. That's minimizing cost, maximizing comfort. That's the ideal point. But I don't have that. There is always a curve or something that cuts that off, and that gives you the trade-off. Here, what is that? Ideal point would be the minimum corresponding to this is somewhere here, and minimum corresponding to deflection is somewhere there. So it will be somewhere here is my ideal point. It's cutting that part off. So here is my Pareto set, right? In fact, I think I have a line. Yeah, that's my Pareto set. So if you can look at this objective space with all your solutions, then you can see where the Pareto front is for only two objectives, maybe three objectives. More than that you cannot. But let's try to understand what's happening. Okay. But the problem with that approach is you need to compute every point. It's an exhaustive search. You don't have time for that. So you need an algorithm that's going to start randomly in this space and going to come to the Pareto set. Now the question is, where is this set here? In this problem, if you look at each of these points and see where they're coming from, they are all from this line. So that's the Pareto optimal set. This is the Pareto optimal front. Okay, or sometimes they call it efficient set. In the MCGM literature, they call it efficient set. So when you start from here, random points, all of these points should try to go towards there. Okay, here. And that's our target. So in this problem, we completely understand where we are supposed to go, what constitutes the Pareto optimal set. In a more complex problems, there is no way of knowing because you'll simply not be able to plot this. But I hope you get the idea of what's happening. Yeah, the important thing is there are a number of solutions that are optimal. So I can have infinite solutions here. If I have a discrete search space, then I will have a discrete number of points. Yeah, efficient set, Pareto optimal set. Okay, now let's go with some definitions and see how can we define Pareto optimal point. A solution X star, which should be part of the feasible region X, is called Pareto optimal if there is no other X, no other solution in the feasible space that is better with respect to all objectives. So if I am here, let's say I am two objective here, F1, F2, and I'm trying to minimize. If you have a point in the third quadrant, let's say if I have a point here, this is better than this, call this A and call this X. X is better than A in F1, right, because it's better, it's smaller F1. X is also better than A in F2 because this is smaller than that. So any point you have in the third quadrant of A is better than A. Does that make sense? Any point you have on the first quadrant here, who is better? Let's call this Z. Is A better or Z better? A is better because A has a smaller value than Z in both objectives. So anything on the first quadrant, A is better. Anything on the third quadrant, that one is better. How about anything on the second quadrant or fourth quadrant? So let's take this point. So this point, call this K, that is better in F1 than A, but worse in F2 than A. Same thing happens here, which means if your point is, for two objective minimization case, if your point is on the second or the fourth quadrant, you are not better than A. In fact, you are equivalent. They are called non-inferior. They are not inferior to each other. They are equivalent. Okay? That's what happens. But this definition clearly says if you are in the third quadrant, then you are better than A. So it says if there does not exist. So let's take this example. Let's take one of these points. Let's draw the third quadrant. Do you have any point of these black dots, because those are only feasible points, right? Do you have any black points on the third quadrant of that point? Call this A. No, right? There is nothing on the third quadrant. That's why A is Pareto-optimal. Let's take a point here. Is there any point in its third quadrant B? Is there or not? Simple yes or no answer. Yes, there are many points, you see here, so many points. Even one point is enough to say B is not Pareto-optimal. You take any other point here, you draw the third quadrant, there is nothing here. So that's why that point is also Pareto-optimal. So you try this trick to any point over here in the F space, you will find that there is at least one point in its third quadrant, and that makes it, again it went away, that makes it not Pareto-optimal. Is that right? Is that clear or not? This is not rocket science, this is simple stuff. Okay, and in 2 dimensions it's very easy to see. Okay, all right. So the set of all Pareto-optimal solutions is called Pareto-optimal set. The set of all objective vectors in the F1, F2 space, they are called efficient set. Okay, let me make it a bit more concrete. So let's say this is my feasible objective space. This have to be always in the objective space before you do all these. So this curved enclosure is constituting all feasible objective vector. Okay, I am deciding whether this point is Pareto-optimal. All I have to do is look into this third quadrant and see, do I have any point? There are lots of points I will have. So this is not Pareto-optimal. If I try A, third quadrant, there is nothing here because all things are here. So nothing here, so this is Pareto-optimal. Yes. How about this point? Is this Pareto-optimal? Simply look at his third quadrant. Is there any point? Where is his third quadrant? Is there any point there? Yeah, there are all of these points. So which means any of them is better than that, so this can't be Pareto-optimal. So no. So Pareto-optimal front starts here and it finishes here at B. And then it starts again at C and it goes all the way until D. This point is not Pareto-optimal. There is lots of points here. This point is Pareto-optimal because there is nothing here. This point is Pareto-optimal because nothing there. This point is not Pareto-optimal because there are lots of points in third quadrant. Clear? So if I give you a shape, can you figure out where the Pareto front is? At least for 2 objectives. Now I can create an algorithm or a definition for any number of objectives. All you have to see is for that point X, and I am checking if A is Pareto-optimal, there should not be any point in this space, right? Okay. There are a lot of ways to figure this out. Let me skip that. a bit more complex here. So let me drilling that. So that's the first definition of Pareto optimality. Second definition is called weakly Pareto optimal. Okay, let's talk about that. Now, if I have this region, let's first think of the Pareto optimal. Pareto optimal goes from here all the way here, and then it starts from here all the way here, right? It ends there. These are Pareto optimal or efficient set in case of objective space. Okay, weakly says a solution X star must be feasible, a set of the feasible set is called weakly Pareto optimal if there is no X in the feasible set such that Fix is less than Fix star for all I. That means if I take a point now here and I go to its third quadrant, there should not be a point, not equality is taken away now. There can be a point on the line here on the axis, but there should not be any point in the interior. On the interior part of the third quadrant, there should not be any point, but there can be a point on the line on the axis. Does that make sense? In the previous one, even a point on the axis is not allowed. If you have, then that point cannot be Pareto optimal. Here it's relaxed a little bit. Since it's relaxed, now you see this point is Pareto optimal, weakly Pareto optimal. Why? Because there are nothing in the interior. There are a few on the axis, but not interior. How about this one? Is this also weakly Pareto optimal? Yeah, there is nothing in the interior, so it's weakly Pareto optimal. So all the previous Pareto optimal are also naturally weakly Pareto optimal, but now there can be more points that are weakly Pareto optimal that are like along the axis, like this one here is weakly Pareto optimal. So weakly will go from here all the way here, starting again here all the way here and going up there. That's the weakly. Weakly kind of takes it little more. So some objective values can be same, but at least in another objective there is a difference, right? So they are called W weak efficient points. They are called weakly efficient points also. Yeah, I'm going to leave the strictly ones. Yeah. Third, we're going to talk about properly Pareto optimal. So let's think of an objective space that is like, these are hypothetical. So we have this as the feasible region. Z is the feasible objective space. Where is the first, let's talk about, where is the Pareto optimal set or efficient set? I'm minimizing both F1, F2. Let's make it a bit interactive so you also understand. Which one? Z star, which means just this point? No, there will be a Pareto set. So which is that? It has to be one of the boundaries, right? The Pareto set is always the boundary of the objective. So which boundary? Is it this one? Is it this one or is it this one? The curve one, because that, if you take any point here, there is nothing on the third quadrant. So the entire thing is my Pareto optimal or efficient set. How about weakly Pareto optimal? Which part? No, there is no weakly. No, I said Pareto optimal set is by default weakly Pareto optimal, right? It's the definition says that, but there could be some additional stuff. But is there any additional stuff here? So if you say, okay, you are confused between this point, let's say whether this point is weakly or not. So let's draw the third quadrant. There should not be any point in the interior of this. So is there any point in the interior? Yeah, so this cannot be, like these are all interior, so this cannot be weakly Pareto optimal. So in this case there is no extra like horizontal or vertical lines, so the same line is also weakly Pareto optimal. They are the same. Pareto optimal set and the weakly Pareto optimal set are the same. Make sense? Now we are introducing properly Pareto optimal. Let's look at a point here and compare with point this. Call this A and call this B. Okay. What's the difference between A and B in terms of F1? So obviously B is better than A in F1, right? How much better? This little thing, sorry. This little part. Very small difference, advantage. Little better than A in terms of F1. And obviously A is better than B in F2. How much better? A whole lot. this much better. So, B is better than F1 in a tiny amount, but A is better than B in F2 with a large amount. So, are you interested in both, or which one? Do you have any preference for A and B if you are a practical person? Would you like A to implement knowing B exists, or B to implement knowing A exists? Let's be practical. How do you make that decision? How much I am sacrificing, right, versus how much I am gaining. So, let's say I am deciding, what if I choose A and ignore B, how much I am sacrificing? Very little of F1 I am sacrificing, but I will have to give away, I will have to increase my F2 like a large amount. So, if this is like environmental effect, let's say it goes between 0% to 100%, and this one is, let's say, cost. This one is cost, and let's say this goes between $1,000 to $10,000. So, when I am here, let's say this is a $1,200 solution, and this one can be 1,000. This is less, right? So, let's say 1,190. This one can be, let's say, 80% environmental effect, and this is, let's say, 95% environmental effect. Okay? So, if I implement A, I am making environment, let's say I am throwing 85% of pollution. If I choose B, I am throwing 95% of pollution. So, and the gain, so the gain I am going to make from A to B is only $10, and I am sacrificing 10% of pollution. Am I interested in B or am I interested in A? Is that a difficult question? Shall I make these numbers a bit more? So, you see, so all I am saying is, am I interested in a $10 benefit to screw up the environment by 10%? Yes or no? Will you be interested in it or not? No. That is a very practical answer. No. For $10, I would rather pay $10 more and save environment by 10%. Definitely, right? This is the situation here. So, do you like A or B? A. Why B? Because B is that advantage you are taking, $10 advantage you are taking, because B has $10 less, but your environment you are screwing up more. So, you do not like B, right, when you say that you like that trade-off. So, A is what you are going to go. So, that is the practical aspect called properly Pareto optimal, where you are now looking at the trade-off and in saying both are Pareto optimal. Both, if you put the third quadrant, there is nothing on the third quadrant. Both are Pareto optimal, but one is a bit more preferred because of the nature of the trade-off. The nature of this Pareto optimal curve that makes that. But if you take this point versus that point, if you call this A dash B dash, now you sacrifice a whole lot cost to go to B dash, and you sacrifice almost the same amount of environment. So, now it is difficult to decide whether you are going to choose A dash or B dash. That is a question I am not going to ask you, because it is difficult to decide. You need some more criteria, some more your pocket, your budget, lot of things you have to see there. But this is a very easy decision. Here also it is a very easy decision to make. So, they say, because the trade-off is such that being Pareto optimal, I now have preference of certain Pareto optimal versus certain other. So, we say we are going to restrict it, the Pareto optimal set, to in the middle somewhere where the trade-off is good, like this, not like this trade-off or not like that kind of trade-off. These are not good trade-off. Even I can say no, I am not interested. So, how do we define these bounds? There is a parameter that comes in now. It is the trade-off, the gain, the loss versus gain, and you want to restrict it to certain value. Okay? So, once you specify this, is basically dealing with the slope, and wherever this L and 1 over L slope hits the Pareto front, your target becomes that. So, you have algorithms that will not find the entire Pareto set, but only the proper Pareto set. So, this is called the proper, discard, okay. This is called the proper or properly Pareto optimal set. So, the entire thing is Pareto optimal, entire thing is weak Pareto optimal, only maybe here to here depending on L. There is a parameter that decides, you will have properly Pareto optimal. So for all practical purposes, if you are working with the industry or if you are working in an industry and doing this stuff, you should be interested in finding only the properly Pareto optimal set, because those things make sense. Okay? Yes. So it basically happens where the slope is L and the other side the slope is 1 over L. And as you realize, this only happens when you have a convex Pareto set, right? This proper Pareto has the meaning. Let me skip that part. Now let's come to some algorithms. So those are the definitions, 3 different definitions we talked about. Classical way of doing it, which is the point-based method. I'm going to stop at little after 12. Yeah. So classical way of doing it is you get the multi-objective problem with multiple objectives, as you see there, with constraints and everything. First thing you do, you scalarize the problem into a single objective problem. One simple way you may be sitting there thinking is, why don't I take weights according to the importance of each objective I have in mind. So the objective F1, I am 30% importance compared to others. This one 20%. Like that, the sum can be 1, the sum of the W's can be 1, and I just do a weighted sum. Provided everything needs to be minimized, everything are in the proper scale, same scale, I could add them and minimize only this function. Turns out, yes, you could do. If you minimize this with your favorite single objective optimizer, you will get a single solution, because this one will have a single optimum usually, and that's going to be one of the Pareto optimal point, guaranteed. Okay? Then if you want to find another point, you need to change the weights, and you rerun, you get the next point, and so on and so forth. So here is the principle. If you have 2 objectives, yeah, a little screwed up, 2 objectives F1, F2, you can use W1 and W2. Usually we use W1 between 0 to 1, and W2 can be 1 minus W1. Okay, this is W2. So then you can set that way, their sum is always 1. So if you do that, turns out the theory says that your contour plot of this f function in this objective space becomes a straight line with a slope of W1 by W2. Okay? And then when you minimize, you are basically dragging the line before you leave the feasible objective space. That becomes your optimum. So in your Pareto set, wherever this slope, this line with the slope become tangent, is your solution to the weighted sum. So now if you want this point, what will you do? If you know the Pareto set, you can actually draw a tangent and figure out the ratio of W1, W2, set it up here, run, you will get this point. So by changing the W systematically, you can actually generate. Okay. And this has a proof that you're always going to create a Pareto optimal point. Yeah, there is the proof actually we are talking about. But what this proof doesn't say is, coming from here, if it's a convex set, if that set is convex like the way it's shown, bulging out, convex set like this, then only it works. But for non-convex cases, you may not get every point. So what I told you is, if you use a W1, W2, which are all positive, okay, optimize this function, what the result you are going to be getting is always a Pareto optimal point. But not every Pareto optimal point can be obtained by this method. The reverse is not true, and I'll give you an example here. If you want to find this point, this is, by the way, is this Pareto optimal? How will you check in 2 dimension? Always the third quadrant. Is there any point in the third quadrant? No, so that's a Pareto optimal point. Okay, so this whole red line is my Pareto optimal set. How can I find this by weighted sum? As we just discussed, you need to have a slope. You need to have W1, W2, where this slope, this line is a tangent at that point. So I can figure out what is W1 and W2 and set my weighted sum, but would that be the result? Because remember what I said, the contour is this line, right? So you are coming down this way. When you minimize, is that the one you are going to converge? No, you see, you can go even further and you have these supporting points. So you will end up at D. With this slope W1, W2, this will not be your final solution. Your optimal solution is going to be D. So you will never get this point by the weighted sum approach. And that's true with any other point you take here. That's not going to be the last one. Okay? It's going to be from C to D, and A to N, here to here to here is what you are going to discover using the weighted sum approach, and this whole gap is going to be there. When you run it, you will see this whole gap there, and you will never know, is there actually a gap? Actually, there is no gap. There are Pareto optimal points, but just as your method did not allow you to find them. There are a lot of funny stories. Once you understand the theory, that why I cannot find this, you know. But there are big shots in our field. I'm not going to name. Early on in their career, they probably understood by now. They came up with an algorithm, and they says all theory is wrong. See, here is the result, and they did weighted sum on this and showed points found here. I was very curious, how did they find it? Because theory says no. I looked at what they have done is they set up a weight like this, okay, this weight, and they run the weighted sum using some standard point based methods. They are saving every iteration, 1, 2, 3, 4, they are saving every point. Okay, so you started from here, you go there, 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 go there, go there, go there. Eventually, you are going to get there, right? So this point was there, this point was there in their population, but the final one is your result. We usually print out the final one, but they are saving every intermediate solutions. And then they say, do a check that is anyone is dominating the other. Okay, is anyone in his third quadrant or not? If not, all the ones that are in second and fourth quadrant they keep. Obviously, all of them are going to be in their second and third quadrant, fourth quadrant. So they stay and say, see, I can find it. What is the fallacy there? What is wrong with that method? Theory is still right because you are not supposed to get it, but sorry? Yeah, it's about convergence. So they did an algorithm where they picked points from the intermediate part. So I could do that for any problem, like I have to go to the optima, but I'm saving all my intermediate points, and then I'm utilizing it in my favor later on. I'm saying, yeah, let it go somewhere, I don't care, but my goal is something in the intermediate. That's not a purpose of an algorithm. Algorithm is you write something, you start with something, you end up with something, and then you see what you end up with. You don't pick things from intermediate, right? It's defeating the purpose, but saying theory is wrong is not the correct way of doing it, right? So once you understand these things, you will never do anything like that. But there are all kinds of things in the literature, but once you understand, then you know why they are not able to do it. Okay, I will show you a much better way of doing that. But before that, there are a couple of points that are very important in multi-objective optimization. One is the ideal point, which is if this is my objective space, feasible objective space, usually we represent it with capital Z. If you take the best of F1, can you tell me, okay, let me put some label here, A, B, C, D. Okay, so which is best for F1? This is the objective space. Which point out of A, B, C, D is best for F1? A, right? Because there is nothing below this A. So minimum of F1 is this value coming from A. What is the minimum of F2? B, which is over there. So if I take this F1 minimum and F2 minimum and put them together, I get a vector. So this Z star is basically F1 minimum, comma, F2 minimum. It's a vector I have created. If you have 5 objectives, just take individually optimize every one of them, put them together, concatenate them. That's my point in the M objective space, and I've got the ideal point, which is known as Z star. Ideal point is never achievable, because if it is, then it's not a conflicting objective scenario, right? Okay, so that's very easy to find. There is another point called Nadir point. What that point is the worst corresponding to the Pareto optimal set, not the worst corresponding to the objective space. Let's talk about that first. If I take the worst of F1, that is maximum of F1, where do I get? This point, right? And then worst of F2 is this point, highest of F2. If I put them together, I get the point D. That's not Nadir point. Nadir point is if I know the Pareto set, I will take the worst of F1, which is this value, out of these Pareto sets, Z efficient, and worst of F2 is this one. I put them together and I get this point. That is called the Nadir point. So you see the catch 22 here. To get the Nadir point, I need to know the entire Pareto set. Otherwise, I don't know what is the worst of that. And the reason for knowing Nadir point is to find the Pareto set. So that's the chicken and egg kind of problem. So how is the Nadir point helpful to find the Pareto set? To normalize, okay, the ideal and Nadir point. This could be cost, like I said, $10,000. This could be efficiency like 100% maximum, right? So there is a mismatch in the scale. If I compute any distance between 2 points here, it's basically this one is dominating. So somehow I need to normalize the objectives. If you know Nadir point, if you know ideal point, you can normalize. This one becomes 0, this one becomes 1, this one becomes 0, this one becomes 1. Now the distance is properly calculated. So here is the normalization. Knowing the ideal and Nadir point, you normalize, and this normalization is what is used within every algorithm. Okay. So Nadir point is an important thing to find. There is a payoff table method to estimate Nadir point. And you can use this to find both ideal and Nadir points. So let's quickly see how to do this. You individually minimize every objective function with constraint. So you do constraint minimization with fmin_con or whatever single objective algorithm. So for f1, you find x1. For f2, you find x2. So let's say these points are found. This one is for best for f1. This one is best for f2. Now you compute f1 at that point, f2 at that point, f3 at that point, so on and so forth. You fill this up. Similarly, compute f1 at x2, f2 at x2, fm at x2. Like that you fill this matrix. Is that clear? Each of these points is individual minima of every objective function with the constraints that you have. Okay? If there are m objectives, there are m solutions you found. These are individual minimum. And then at this minimum x values, you compute all objectives. You minimized f1 to get x1, but after you find x1, you compute f2 at that point. You compute f3, compute fm like this. Okay, once you fill that up, can you point me to the ideal point? How will I construct the ideal point? All the individual minima. This is minima for f1, this is minima for f2, this is minima for fm. So if I take this diagonal and construct a vector, I get the ideal point. Clear? How do I get the Nadir point? I take the max of all these f's, put it here. I get the max of all these f2, I get it here. Max of all of these, and I construct this as a vector. That's my estimation of the Nadir point. As if these are all my Pareto points, x1 to xm. Actually, these are extreme Pareto points, and then I am actually taking the worst of each of these points. So that's an estimate, that's never the ideal, and we have lots of examples where this is not the ideal case. Okay, I'm going to leave the example. Yeah. Minimizing, yeah, all are minimizing. All objectives minimization here. So if you have to, if there are some objectives maximization, you have to do minimization. So if you are doing maximization of f1, or let's say fix, that is equivalent to minimization of minus fix. So if you put a minus sign, and I can show you simply, if you have to maximize this function over x, this is your fix, you do a minus of fi is going to be this function. So maximum happens here, that same happens for the minima of this function. So if you minimize minus fx, you will get this point, same as maximizing the original function. So convert maximization problem to minimization problem by multiplying the objective into -1 and then doing this process. Yeah, that's a good point. Any other question? Okay. All right. This is the other method I was talking about that doesn't care whether you have convexity, non-convexity in your Pareto set. This is called epsilon constraint method, where your scalarization is a slightly different way. You pick one of the objectives, f1, f2, f3 to be minimized, and rest all objective you put under a constraint. So for example, I can say minimize f2 subject to f1, which I didn't use here, should be less than equal to epsilon 1. So let's look at that problem. And then you have the other constraints. They have to be, all the constraints have to be there. So here is my feasible z. Now I come and put a constraint on f1 saying f1 should be less than epsilon 1, which means only this part is feasible now because I have added this constraint. Now I am minimizing f2. So what value I am going to get? what will be the result of this problem? C, right? Because this is the feasible region, I am minimizing for F2, I will get this, which was difficult to find using weighted sum. If you want this point, all you have to do, put a epsilon here, choose this epsilon here and put it over there, and this becomes your feasible region, and this will be your solution, which was difficult to find. So this algorithm has both way proof that for epsilon 1, any value of epsilon 1, either you get a Pareto optimal point or you get an infeasible point. How infeasible? If I put my epsilon here and I am saying less than this is feasible, there is no feasible space. So you will never get any feasible solution. If you put your epsilon here, what happens then? The entire space is feasible. What solution you are going to get? D, when you minimize F. Whether it's here or here or here, you always get D. But if you fall in this between ideal and nadir point, you see how ideal and nadir point are important now. If you put your epsilon here, anywhere, then you get one of the Pareto points. Okay? So knowing some idea about ideal and nadir point helps you choose where to put your epsilon. Okay. And this also has a proof that any Pareto optimal point can be found by this method, which was not guaranteed by the weighted sum approach. So if I have to pick one of the two methods, weighted sum versus this, I would choose this. This one adds a constraint, and many people in optimization don't like constraint because that's difficult to handle, right? But if you use GA, we talked about the penalty parameterless approach today. Okay, these are all the proofs, I'm not going into the details. And this problem, if you use weighted sum, this is what you get, you see, here and few points here. You don't get anything in the non-convex part, but if you use epsilon constant, you can get everything. Okay, let me skip some of these. There are other methods like Chebyshev method and all that. Yeah, it's too much about different techniques of finding them. Just to say that value function is also used quite a lot. Value function is, you have two objectives, cost, let's say, versus environment, but you say you have in your mind, you have a combination of the two. Some combination, let's say cost over environmental effect versus divided by cost. You think that per unit cost, how much environmental effect you have. That's something is important to you. Although you want to have two objectives, but this is really what you are trying to. So that becomes your value function, U. And then you can simply optimize this as a single objective. But then you got to be absolutely sure that this is what you want. See, what happens in practice is not one designer or user is making decisions on these things. There are several persons in a group. Maybe your boss will ultimately have the power to say, what you think as a utility may not be what your boss thinks as the utility. And that's where the problem comes in arriving at a good one. So the best strategy is find a set of points and then sit with every decision maker and decide, come up with a compromise solution, because now you have solutions. And that's exactly what the automakers have done, right? When you go to the showroom, you see all of these cars, and you being the decision maker with your family members, you go and make a combine, or your friends combine decision of what you want to choose. Let me skip all that. This is an important one, achievement scalarization function. Okay. So what's happening here is this is another way to scalarize. So we are still on the point-based approach. We're still not evolutionary method yet, but this is a very important one. So in this, if this is my Z, where is my Pareto set? It starts here, where the slope is 90 degrees, and then you come all the way. Because these are any of these point, third quadrant, there is no point, and up to here. This is my entire Pareto set, or sometimes we call it Z efficient. Okay. Now, I'm not interested in the entire thing. I'm interested in a part or maybe a point on it. How do I say which point? You come up with an aspiration point called Z bar, which is saying, I have a combination of the two things in mind. I can spend $500 to get an environmental effect of, let's say, 50%. That is what I'm thinking. I'm in my mind that I want to pay $500 to get this kind of gadget in for my home that's not going to throw more than 50% of pollutant. I'll be happy with that. So that's your aspiration point. Now you see, in this case, all feasible solutions are here. nothing is on your point. So I will disappoint you. I will tell you, sorry, for this problem, I cannot give you such a solution. You have to increase your dollar value or reduce the expectation. If you keep your dollar value, I can give you a solution. The earliest one I can give you is maybe 80%. Are you happy? You say no. Then you say you increase to maybe $1,000. Maybe then I can give you one with 70%. If you want 50%, you need to spend at least so much dollar. So that's the kind of way I decide what I can afford and what I'm looking for. You get a point. You can get multiple points, but let's say with 1 point. What this guy Wierzbicki is a genius, Wierzbicki, from Polish researcher, he came up with is that he says, once you give me that, I'm going to formulate a problem, like this one, called ASF, Achievement Scalarizing Function, that's going to pinpoint 1 point for my Pareto, guaranteed to be a Pareto point, but it's kind of closest to this point in the sense of some distance, okay? And this is the problem you solve. You can give different weightages for every objective function that you have with this W. Z bar is your point and F is your objective function as a function of X. When you solve this problem, you get this point Z dash. Okay, so that's saying I cannot give you what you are looking for, but the nearest one I give you is Z dash, which means you have to spend more money and you have to sacrifice on your pollution. Okay, I would have been happy if he stopped his paper there, but now he talks about, okay, now that you get that, with this you can construct another aspiration point by taking horizontally from here, keeping the same F2 and keeping this F1, I get a point, and I can get one other point here this way, and I can repeat the process and find another point. Repeat the process, solve this problem with different Z bar, and I get another point. And then I could repeat the process, I get another Z. Okay, so all these I could do another Z. So I can keep doing it. So basically it's talking about populating this region, which is close to this. It immediately caught my attention that he is using point-based method repeatedly to find out a region, not the entire Pareto set. With this process, you can never get a point here, although these are Pareto optimal, right? These are Pareto optimal. You'll never get there because your interest is in here. But he's not giving you one solution, he's giving you a number of solutions there. I said, hey, I could do this much better with an EMO, evolutionary multi-objective method, which we'll talk about, where each of these I can find, multiple of them I can find in one go. So that's how we figured out what they do, what is their principle, and they are handicapped because they are using point-based methods one at a time. We can speed up by doing evolution. So we'll come back to that later. But this is a nice way that you can choose. So you can use this method to pick a solution. Let's say by EMO you found lots of points here, okay? And now somebody comes and says, here is my aspiration point. Can you pick a solution for me? Yeah, you can find, instead of maximizing, you basically do a selection. Choose from it that's going to do minimum value of this out of all of these, and it's probably going to be that point. Okay, so that's a way we often choose a solution. I mentioned that we'll talk about some MCDM, multi-criteria decision making. This is one of the methods that decision makers provide their aspiration point, and we go and pick a solution from our Pareto set using these criteria. Clear? Okay, there is a augmented ASF with a little slope you get. Let me not get into that. Okay, at this point, if we need, we'll talk about later. Okay, there are some mathematical underpinnings. Like if you have this problem, there is also theory, like we have KKT condition. It's called Fridtjohn necessary conditions with a very similar structure as you see from before, like the Kuhn-Tucker conditions. But now you have multiple objectives. Each objective will have a gradient. So you need another set of Lagrange multipliers. Okay, so similar theory continues here. In case of convexity, a KKT point becomes your one of the Pareto optimal points, right? And then there are weakly definitions, proper definitions as well. So these are sufficient conditions, again for weakly and Pareto, very similar, but then they relax a little bit over there on the conditions on the lambda and mu. Again, I'm not going into the details. When you have free time, you can look into this if you're interested. Okay, so what I introduced to you now is multi-objective optimization basics. Okay, the main result is that they come up with not one but multiple Pareto optimal solutions. There is trade-off between them. You can either find the entire Pareto set one by one if you are using point-based methods, or we'll talk about tomorrow evolutionary way of doing it, then you find the entire Pareto set. But then you need to pick, once you choose all of these solutions, you need to pick one. One I just introduced you, this ASF, by which you can pick one and you are driving that, you are providing that Z bar, right? But the essential part of point based is you have to do this again and again, and that is cumbersome. Several methods exist for that, but we'll talk about the EC method later. Just to finish up, I want to talk about one slide which I left, yeah. So, let's say this is my Z bar and here is my Pareto set with the bold line, and I use weighted sum or epsilon constraint. Let's say this is my target. This is where I'm going. So you start with a single point, right? And then your goal is to get to that. So you have done an epsilon constraint or a weighted sum. So your whole space is such that this becomes your target. So in that process, you do several iterations and converge. You are going through local minima, you are going through infeasible region, another infeasible region, maybe another local minima. Finally, you come here. At the end, you declare this is a solution. Okay, fine, that's the end of it. Now you change your epsilon. Let's say you change your epsilon or change your weights. Then let's say this becomes your target. You start from another initial point. Same complexities, infeasibility, local, isolation, all these you have to learn again, because this run is gone. When you have terminated this run, everything is gone. There is nothing in the memory. You restart, you have to re-understand how to solve the problem. Your algorithm has to be as efficient as it was there. For the third problem, same thing. If you want to get 20 points, you have to do it 20 times. Okay? Sometimes you may be failure, and a lot of people will say, oh, when I do this many times, I get a point here, I get a point here, but another time I get a point here, another time I get a point here, another point here. And then I see that this point, this is already dominating. Dominating means this is in its first quadrant, so which means this is better. So this was useless. This whole run was useless, simply because it got stuck in one of the maybe local optima or on a boundary, constant boundary, it got stuck. That run wasn't lucky and it couldn't go. Some parameter setting you have to change to make it to work. So it's a lot of work, let me tell you. If you want to do one by one by one by one and get a smooth Pareto front, it's very difficult. So that kind of builds up why we need other methods where parallelly we are going to find multiple points. So even if we find multiple points, some of them converging, some of them not there, but close to it, but let's say we find 10, 20 points, okay? Now I can take one of these ASF or something and go to the Pareto front. Now I can do local search and converge to the Pareto set. This is a much better approach. So you start with this evolutionary approach and then finish up with these multiple, each point as an initial point, you just finish up. That's a much better approach. Okay,